Good morning, everyone. Today I will present our research on improving the mechanical performance and sustainability of concrete containing recycled concrete aggregate through silica foam slurry treatment and steel fiber reinforcement. The construction industry generates enormous amounts of construction and demolition waste, while simultaneously consuming large quantities of natural aggregates. In Peru, thousands of cubic meters of this waste are produced every day, creating significant environmental challenges. Although recycled concrete aggregate is a promising sustainable alternative, its application is often limited because it reduces the compressive strength of concrete. Therefore, our research aimed to overcome this limitation by treating the recycled concrete with silica foam slurry and reinforcing the concrete with steel fibers. The objective of this study was to evaluate whether concrete containing 50% recycled aggregate could achieve equal or better performance than conventional concrete while reducing environmental impact. Four concrete mixtures were designed according to ACY 211 recommendations. The first was conventional concrete and served as the control mixture. The second one incorporated 50% of recycled concrete aggregate. The third one included RCA treated by immersion in a silica foam slurry for 24 hours. And the fourth one combined the silica foam treatment with 1% steel fiber reinforcement. The experimental program included material characterization, slam testing, compressive strength testing at 14, 21, and 28 days, and finally a carbon footprint assessment. Regarding fresh concrete properties, the control mixture, the RCA mixture, and the silica foam treated RCA mixture all achieve plastic consistency, with slam values between 3 and 4 inches. The silica foam treatment could be ideal for building frames. However, the addition of steel fibers reduced the slam to 2 inches, resulting in a dry consistency, best suited for slabs or pavements. We can see here all the results obtained on the compressive strength test. As expected, replacing natural aggregate with untreated RCA reduced compressive strength by approximately 20% compared with conventional concrete. However, after applying the silica fume slurry treatment, the results improved significantly. At 28 days, the treated RCA mixture achieved an average compressive strength of 302 kilograms per square centimeter. This represents a 21% increase compared with conventional concrete and a 46% increase compared with the untreated RCA mixture. These results indicate that the silica foam treatment effectively improves the microstructure of recycled aggregate by sealing pores and strengthening the interfacial transition zone. Also, it's important to analyze the image below, which exemplifies how the failure goes on. The silica foam mix localizes failure to corners due to intense internal densification, leaving the core structural geometry intact. The mixture containing both silica fume slurry treatment and steel fibers reinforcement achieved a compressive strength of 265 kilograms per square centimeter, which remained 6% higher than the conventional concrete and 28% higher than the untreated RCA mixture. Although this result was lower than the silica fumes only mixture, the steel fibers improved the failure behavior. Instead of experiencing sudden fragmentation, the specimens maintain their integrity after cracking because the fibers breach the shear cracks, showing a more ductile failure mode. This behavior is particularly beneficial in seismic scenarios because it can provide additional warning time before the structural collapse. In addition to improving strength, the proposed mixtures demonstrated environmental benefits. A carbon footprint analysis was performed using emission factors associated with all the materials. See on the presented table that the RCA emission factor is lower than the coarse aggregate factor, and also see that the silica fume emission factor is lower than the cement one. The results showed that mixtures that use 50% recycled aggregate and 10% of silica fume generated lower carbon emissions than conventional concrete because carbon dioxide emission factor were lower than the coarse aggregate and the Portland cement, respectively. The silica fume treatment mixture reduced the carbon dioxide gas emissions and also improved the mechanical performance of concrete. Therefore, the proposed solution contributes not only to improved mechanical performance, but also to waste reduction and resource conservation. In conclusion, this research demonstrates that recycled concrete aggregate can be successfully incorporated into structural concrete when appropriate treatment methods are applied. First, the silica fume slurry treatment recovered and even exceeded the strength of conventional concrete, surpassing on 21%. The addition of steel fibers improved post-cracking behavior and structural integrity, adding vital resilience against seismic scenarios. Furthermore, the proposed mixtures, with the replace of 50% recycled aggregates, reduce carbon emissions while promoting the reuse of construction waste. Therefore, this approach represents a practical and sustainable alternative for future concrete applications and contributes to the development of a more circular construction industry. Thank you very much for your attention.